From the previous example, what we found was this interesting relationship between the electric and magnetic field measured in a frame S and the fields measured in a frame S bar, where S bar is moving relative to S with a velocity v. And so these are the relationships we found, assuming that the velocity is in the x direction. But what you get is almost kind of a Lorentz transformation where say the electric field in the y component measured in the S bar frame, so I'll highlight it right here, is a mixture of the electric field and magnetic field measured in the S frame. And so what we can think of now is the electric and magnetic field measured in different frames kind of mixed together. Or a better physical picture is that electric field phenomenon in one frame can be seen or measured as magnetic field phenomenon in another frame. That means we probably can combine our ideas of electric and magnetic field into a single entity. And so since we have this kind of linear combination of fields, it lends itself really well to a matrix approach. Can we write down a large transformation matrix that would combine the electric and magnetic field in one frame with the fields in another frame? And so what physicists have come up with is something called the field tensor. And so the idea is that you can now write down this tensor, which will combine both the electric and magnetic phenomenon, and it's going to have it's going to be a tensor, a rank 2 tensor, because one index is for one frame and one index is for the other frame. And so we usually write this as F. That seems like a good symbol to use for a field. With two indices, mu and nu. So these would be 4-dimensional indices because in special relativity we combine, say, time and space into a 4-dimensional object. And so like I said, it's going to have two indices, mu and nu. One index is for one frame, the other index is for the other frame. And then I'm going to write down this 4x4 matrix as 0, Ex divided by C, Ey divided by C, Ez divided by C. So that's the first row, minus Ex divided by C, minus Ey divided by C, minus Ez divided by C. And so let me extend this bracket thing a little bit. Zero, zero, zero. So it makes sense to put the electric fields on the, say, the 0th row and the 0th column, because in our equations, there's a 1-to-1 correspondence between the electric field in like E bar and E. Now, with the magnetic field, if we go back out, we notice that there is this kind of cross product where the Y component of the electric field matches with the Z component of the magnetic field. So therefore, they're going to be on off-diagonal elements. And what we would get is, if we compare with our example, BZ minus BY, and then BX here. And then over here, you would get minus BZ, positive BY, and minus BX. Okay, so that fills out the matrix right here. And that matches with the example that we did before. So what you'll notice is, filling this out just from, say, analogy, is that, like I said before, F mu nu is a rank 2 tensor. So that's pretty obvious. And what you'll notice now with the way that we've placed the minus signs is that it's an asymmetric tensor. Oh, sorry, antisymmetric tensor. So what does that mean? Well, if I take the transpose of it, I would get minus nu mu. So if I exchange columns and rows, I would have to put a minus sign in front of it. So that's what makes it an antisymmetric rank 2 tensor. So now what we have in the single object here is a combined idea of fields that we have in single object F mu nu, which is a combination of both electric fields and magnetic fields. And we can use it now to transform from one frame of reference into another. So it matches perfectly with special relativity. And so what you can think about is I kind of biased this result by saying the electric fields are one-to-one correspondence in one frame or the next. Say we'll go back and look at the Z component of the electric field in the barred frame is just gamma times the Z component in the unbarred frame. Now, we could have taken the other equations. If we look at the Z component of the magnetic field, the Z bar, so the magnetic field, the Z component of the magnetic field in the barred frame is equal to gamma, the magnetic field Z component in the unbarred frame. So we could have constructed our tensor like that way, or I could say we can write another tensor which would match with our idea of the magnetic field first and the cross terms being electric field. So we could do that just by inspection, like we did with the F mu nu, or if we look at it, we can transpose things and say that EC becomes B and B becomes minus EC. Minus because, again, it's an antisymmetric tensor. And so what you get is another tensor, which we'll call G mu nu, because it's the next letter in the alphabet, and its components are 0, bx, by, bz, minus bx, minus by, minus bz, 0, minus e, z over c, ey over c, and then we would have a ez over c, 0, ex over c with a minus sign, and then a 0, and then this one would become minus ey over c, and this was ez over c. Okay, so now we have a complementary rank 2 tensor, which we call the dual tensor, because it does kind of the same job as the field tensor F mu nu, except for the fact that now it gives us basically the other set of equations. So the F mu nu, you can think of giving us the equations for the electric field transformation. The dual tensor now gives us the equations for the magnetic field. Okay, so now what we have is our two field tensors. We have F mu nu and we have G mu nu. And with them, we're going to hopefully show that you can write down Maxwell's equations now in this tensor formalism. Okay, so before we do that though, what I'd like to do is to kind of write down electrodynamics in tensor notation. So let's write down electrodynamics as tensors. So the things that we have to worry about are the charge, the volume, and the speed. the relative speed between the two frames. The charge density is charge divided by volume. The current density is charge density times the speed. Now, in the proper frame, so basically the rest frame of the charge, like so, then I'm going to write this as rho 0, which is Q over V0. So since V0 is made of lengths, the length contraction is going to modify V. Now, that length contraction is essentially going to give you this times V0, which means I can write down the charge density now as the charge density times gamma, like so. And that means that the current density is going to be rho 0 U over 1 minus U over C quantity squared. So basically, that gamma factor applied to it. So if you look at this now, this is essentially now a modification of the velocity. And so I could write my current density as a 4 vector, so 4 components to it, the charge density times, say, a proper velocity, eta. So if I do that, then my current is now a 4 vector, like I said before. The time component is the speed of light times the charge density, and the spatial components are just the x, y, z components of the standard current density. Which means I can now write down my continuity equation. The divergence of this spatial part of the current is equal to minus the time derivative of the charge density. And since current and charge density are now one and the same 4 vector, I could bring this together, or I could write it out explicitly as minus 1 over C which is the same thing as writing minus the derivative of the time component of space-time. Okay, which means I can pull this all together. And what I get is a divergence of 4 vectors, like so, or as I like to write it, I kind of like to avoid putting indices in denominators, and so I would write it as the dot product of the derivative operator with the current. So that right there, in just essentially 2 symbols, gives us the same continuity equation written down in Gibbs notation as that right there. So this is the continuity equation in tensor notation. Okay, so in the next lecture, what I'm going to do is I'm going to move on and give you Maxwell's equations in tensor notation.